Thanks for watching my video today. Let's prove another integral representation for the Euler-Mascheroni constant. Okay, then is prove that the integral from 0 to 1 of 1 upon 1 minus x plus 1 upon log x, where log is ln x, okay, dx, which is the Euler-Mascheroni constant. So this integral representation is by Euler, okay, this is by Euler. Now to prove this, now let our integral to be I is equal to integral from 0 to 1 upon 1 minus x plus 1 over ln x dx. Now we can put the integral sign one by one, okay, which is integral from 0 to 1 over 1 minus x dx plus integral from 0 to 1 upon ln x dx, okay. Now let's use substitution method. Then is put log x equal to ln x equal to negative t, and 1 minus x is equal to t. So here if you find out x is equal to e to the negative t here, and dx is integration of differentiation of exponential function is negative e to the negative t dt, okay. This is the derivative of e to the negative t, and derivative of this one is going to be negative dx, which is equal to dt, implies that multiply both sides by negative, so dx is negative dt. Why we put here negative? Because of this or limit, okay, because of our limit, so that's why. Now when for this, then is the second integral. For this, when x tends to 0, when this is 0, then t will be what? Infinity, right? So in order to get this, so we are using negative t, okay. When x tends to 1, then t will tends to 0, and similarly here, when x tends to 0, t will tends to 1, right? And when x tends to 1, then t will tends to 0. That's it. Now our integral I is equal to this one, the integral from 1 to 0, right? 1 to 0 of dx is negative dt, right? Negative dt upon t plus integral from negative infinity to 0 of negative, this is negative, okay, negative e to the negative t upon negative t dt, which is equal to, because of our integral this, and is the integral of a to b f dx is negative time integral from b to a f dx, okay. So due to this property, so we can interchange this. Because of this negative, we can interchange the upper and lower limit, so we can get integral from 0 to 1 dt upon t, and minus 1 minus is plus minus minus, okay. And because of this negative, so this limit will be interchanged here, and is integral from 0 to infinity e to the negative t upon t dt. Now again, in the previous we have proved that the limit representation of exponential function then is e to the negative t, is we have already, so okay, we are going to use that. So I is equal to integral from 0 to 1 dt upon t, same thing, minus integral from 0 to infinity of 1 upon t, and limit representation of e to the negative t is nothing but limit n tends to infinity 1 minus t upon n to the power n dt, okay. So this is nothing but or e to the negative t, okay. Now let's bring the limit here. So I is equal to limit n tends to infinity, the integral from 0 to 1 dt upon t minus integral from 0 to here, since n tends to infinity, so since this is infinity, so we are going to replace by n, right? This is just the same thing, 1 minus this one, 1 minus t upon n to the power n upon t dt, okay. Now which is I is equal to limit n tends to infinity, integral from 0 to 1 dt upon t minus, so we can interchange 0 to n by using this property. The integral from a to b is equal to integral from a to c plus integral from c to b, okay. So using this property, so 0 to n is same as 0 to 1 to 1 to n, right? So that's it. So I is equal to limit n tends to infinity. So since these two integral upper and lower limit are the same thing, so let's combine them. So integral from 0 to 1. Here is 1, right? 1 minus d by n or to the power n upon t. dt common, right? Denominator t common, so dt minus integral from 1 to n, 1 minus d by n to the power n upon t dt. Now I is equal to limit n tends to infinity, integral from 0 to 1, 1 minus d by n to the power n upon t dt minus integral from 1 to n of 1 minus d by n to the power n upon t dt. Now adding and multiplying, no, adding and subtracting this one, okay? Then is integral from 1 to n dt upon t, right? So that we can make like this, okay? So let's continue in here. So this is the continuation part here. So our integral I is limit n tends to infinity, integral from 0 to 1, 1 minus d by n to the power n upon t dt. And here I'm going to take plus first, okay? Plus the integral from 1 to n of, here is 1 minus d by n to the power n upon t, right? This one minus, and integration of this one, integration of 1 by t is nothing but log t, right? So the upper limit is 1 to n, so log 1 minus log 1, right? Since we know that log 1 is 0, therefore we are left with only log 1, okay? Natural log 1. Okay, now, okay, which is I is equal to limit n tends to infinity of, so because of this integral, this property we have, so we can combine these two again. 0 to 1 to 1 to n is same as 0 to n, right? So integral from 0 to n, 1 minus d by n to the power n upon t dt, because the integrand are the same thing, dt minus log 1, okay? Now let's do substitution method. Now put t by n equal to x, okay? Implies that dt is and dx, and when t tends to 0, x will tends to 0, right? When t is 0, x is 0, and when t is n, then x will be 1, right? That's just here you can say that t is equal to nx, okay? T equal to nx, right? Therefore I is equal to limit n tends to infinity, integral from 0 to 1, 1 minus t by n is x, right? X to the power n upon t is nothing but nx, right? Nx into, and dt is n dx, right? Minus log n, log n, and these two cancel out, right? So then is I is equal to limit n tends to infinity, integral from 0 to 1, 1 minus x to the power n upon x dx minus log natural logarithm n. Now let's do substitution again. Put 1 minus x, this part here, is equal to u, implies negative, if you differentiate it, negative dx is du, or multiply both sides by negative, so dx is negative du. Now when x tends to 0, then u will tends to 1, right? And when x tends to 1, u will tends to 0. That's it, right? Now I is equal to limit n tends to infinity of, so this one will be when x tends to 0, u will tends to 1, right? Integral from 1 to 0 of 1 minus x is nothing but u to the n upon 1 minus u. Here if you find out here x, then you get 1 minus u is equal to x, okay? And dx is nothing but negative du, right? Minus log n, which is equal to limit n tends to infinity, integral from 0 to 1. Because of this negative, so we can apply the property of definite integral, this one, okay? And then you'll get what? The integral from 0 to 1, 1 minus u to the n upon 1 minus u du minus log n. Now we know that, so if you see this the integrand here, this one, if you see this is nothing but GP, okay? Geometric progression. So since sum from k equal to 0 to n minus n, x to the k is nothing but 1 minus x to the n upon 1 minus x. Okay, this is or geometric progression GP. Okay, so I is equal to limit n tends to infinity. So because of this, we are going to replace by this summation, sum from k equal to 0 to n minus 1, the integral from 0 to 1 u to the k du minus log n, which is limit n tends to infinity, sum from k equal to 0 to n minus 1, integration of u to the k is u to the k plus 1 upon k plus 1 from 0 to 1 minus log n. So which is I is equal to limit n tends to infinity, sum from k equal to 0 to n minus 1 upon k plus 1 minus log n, right? So which is, we can change this one is as I is equal to limit n tends to infinity, sum from k equal to 1 to n of 1 over k minus log n. So this limit is what we call the Euler-Mascheroni constant, okay? This, which is represented by the small gamma, okay? Hence, or original integrate and is or integrate this one. This will be the integral from 0 to 1 of 1 upon 1 minus x plus 1 upon natural log of x dx is the Euler-Mascheroni constant. So this integral is represented by Euler himself, okay?